Hi everybody. Today's lecture we're going to look at curved mirrors and how they affect light and images and things like that. And in particular we're going to do it through a way called drawing ray diagrams. We'll deal with the math version later on. But before we get started, you really need a couple things for this. One, you should have downloaded or hopefully you've downloaded the copy of ray diagrams that is available on my website. And the other thing is you will need a ruler, and I recommend a pencil with an eraser in case you make a mistake. The nice thing about this is once you get it down, once you practice it enough, it's actually pretty easy to do. Okay. So to begin with, we're going to talk about something called a concave mirror. Okay. And a concave mirror is an inward curved mirror. Kind of like this, curved in this particular way. Now, this is the type of thing we don't see too often. It's be like looking at the inside of a spoon if you want to look at it that way. But it's this kind of type of mirror. Now, because of its curvature, it has something called a focal point on that principal axis, on that line that bisects the mirror. And then it also would have a center. And basically here's what I mean. If this mirror were to be drawn into a complete circle, then like any circle, it would have a center point, center of its location. But halfway from the center to the mirror, the curved part of the mirror, is what is known as the focal point. Okay? Now, the focal point means this. Anytime light rays come in parallel to the principal axis, in other words, all these parallel light rays coming in, okay, and they're parallel to, remember, again, this line here is our principal axis. Well, by the law of reflection, because of the way it's curved, these lines would bounce off the mirror and be reflected through the focal point. Okay, so all parallel light rays, rays parallel to the principal axis, are focused or converge towards that particular focal point. Okay, and again, keep in mind that the center is always twice the distance to the focal point, or the focal point is 1/2 the radius of curvature. Okay, that's the other way of looking at it. Focal point is 1/2 whatever the radius is of your curved mirror. Now, interestingly enough, we'll get different looking images depending on how far in front of the mirror we're actually located, where our object is. Now, to understand this, we're going to do this thing called ray diagrams. Now, people teach this different ways, but I basically focus on two locations throughout all of ray diagrams: C, the center, and F, the focal point. C and F, C and F. And so the way this is going to work, first of all, we're going to draw two sets of rays. The first one we draw from the top of the object through C, the center. Wherever C may be located, wherever the object's located, we go from the very top of that object through C. And then the second ray, we're going to draw straight across parallel to the principal axis. So straight parallel to the principal axis, and then we'll allow it to reflect through the focal point. Once we've drawn those, our image will be located wherever these real light rays cross, or if we end up with some virtual light rays, where they appear to cross. Now again, a lot of this might not make sense until we actually do some drawings. So let's take out our ray diagram pictures and look at the concave mirror. Okay, so here is our concave mirror. And to start with, I've placed an object far out from the mirror, okay, beyond where even the center of curvature is. Now, the first rule of ray diagram, I'm going to take my ruler and I'm going to draw a ray from the top of the object through C, through the center. My next ray, I come from the top of the object straight across parallel to the principal axis. And then, because it's a curved mirror and the way it's curved kind of down towards the focal point, I bounce it off the mirror and down through F. Now, notice that there is a point where those light rays intersect. Well, that's where my image forms. Now, my image, I have to draw it from the principal axis to the location where they cross. Okay? So that's the image. Now, let's look at that image. First of all, it appears out here with the object in real space. That makes it a real image. Okay? If we had a screen, we could actually project that image onto that screen right there. Notice its orientation, though. It is inverted. Okay, it's upside down. Now its size. Now remember, there's a certain height h and a certain height h prime. If you measure it with your ruler, you'll find that h prime is less than h. So it is a reduced image. Or remember, magnification was the ratio of h prime to h. So the magnification here would be less than 1. Okay, so that's basically how you draw that. Okay? Now, let's try another one. Here, my object is located right at the center of curvature. Okay? Now, let's draw a ray diagram. Now, remember your rules, C and F. Well, since the object is located at C, that means I've got to come from the top of the object straight down through C. Okay? Always through C, no matter where it is. The second one, I'm going to go from the top of the object straight parallel to the principal axis. I'm going to bounce off the mirror and go down through F. Now you'll notice that they intersect right underneath C. And so my image has to be formed also right at C. Okay? Now, that image is still a real image. Okay? It's out there in real space. Its orientation is still inverted. And if you were actually to measure this and you did it correctly, we would actually find that it's equal in size. In other words, it has a magnification of 1. Now you've also noticed that there's these distances. Remember we had this distance s for the object distance, and we have this distance s prime for the image distance. Notice that those distances are also equal. Good. That'll be important kind of in the math way of doing things later on. Let's move to the next one. Now, here I've moved closer to the mirror. I'm between C and F, which means for my first ray, which is from the top of the object through C, I've actually got to go backwards to get through C. But then again, my next one, so first one's through C, next one straight across parallel to the principal axis, bounces off the mirror and through F. Now notice I've got to actually extend my lines a little bit here, okay, so that my image is forming way out here, very far away. Now it's still a real image, okay? It's still out there in real space. It's also still inverted. But now it's clearly an enlarged image. Okay? Its magnification is much greater than 1. It's a larger image. Now, this next one's going to be interesting. Here I'm right at the focal point. Okay? So, first line from the object through C. Second one, second ray, straight across, parallel to the principal axis, bounces off the mirror through F. Now, you'll notice that those are parallel lines, which means they can never cross, which means there's actually no image formed. All you would see is sort of a blur in the mirror. Okay, there would be no coherent image, but only when you're right at the focal point. Only when you're right at the focal point. Okay, our last example, now we're between the focal point and the mirror. Our first ray from the top of the object through C. Our second ray straight across, then it bounces off the mirror through F. Now once again you can see that these lines don't come together, but they're not parallel, which means they do come together. But it turns out where they come together would occur if you were to trace them backwards from that location. In other words, follow the line instead of forward, follow it backwards. And what we find is there is an actual sort of intersection back here. Okay. Now I drew dotted lines because this is in virtual space, and in fact this is a virtual image. This one would not be able to be projected. It's in virtual space. I draw dotted lines for virtual, that's the way I was taught. It's now upright, and it is clearly enlarged, okay, with a magnification greater than 1. So those are the 5 different scenarios you can have for a concave mirror. And notice it produced very different results depending on where you were in front of the mirror. The other type of mirror, curved mirror, is called a convex mirror. And this is an outwardly curved mirror. And because of its curvature, the focal point lies behind the mirror inside virtual space. So the focal point is always considered to be negative for a convex mirror. So this is what the convex mirror looks like. It's curved outward like that. This is the type of mirror you often see maybe in the corner of a store that's heavily curved in that way. It's also the mirror that's on the right side of the car, where you see the words written, "Objects in the mirror are closer than they appear." Might be a reason why. Now because it's curved this way, the center and the focal point are in virtual space, on the virtual side of the mirror. Now also because of its curvature, if we have light rays that come in parallel to the principal axis, well, because it's curved outward like that, that's the way it's going to reflect the light. So light rays bounce off of it in a way that makes them appear as if they were originating on that inside virtual focal point. So where the concave mirror kind of converged light towards the focal point, the convex mirror diverges light away from the focal point, spreads it out. Now, how does that affect our sort of ray diagrams? Well, we're going to look at the same 5 situations for a convex mirror. Now, the rules are still the same. The first ray goes from the top of the object through C, the center of curvature. But C now, for this mirror, is way over in virtual space. So I've got to draw my first ray from the top of the object all the way to C. Okay. Now again, when I go into virtual space, I do dotted lines, the way I was taught. My second one still goes straight across, parallel to the principal axis. Now, again, the F for the mirror here is on the inside, but it doesn't go through it. Remember, because of its curvature, it appears to be coming from it. It bounces off the mirror from it. Okay. Now, there is an intersection point. Okay. These lines tend to intersect right in here, inside virtual space, which means it is a virtual image. Okay. It appears inside the mirror. It can't be projected onto a screen. It's upright, and it's clearly reduced, smaller. Magnification less than 1. All right, let's look at another one. Now, notice I put it on 2F. In other words, the same distance C would be on that side of the mirror. So let's draw our ray diagrams. Again, we start from the top of the object, and we're going to go to C through the center. The next ray, straight across, parallel to the principal axis. And then because of its curvature, it reflects it away from that focal point. And again, my intersection appears to occur somewhere right in here, which gives me strangely enough, the same type of image again. Virtual, upright, and reduced. Magnification less than 1. Well, guess what? The only type of image you can produce for a convex mirror is a virtual, upright, reduced image. All the images are in virtual space. You can only produce one image. Now, if you kind of go back to that mirror on the side of the right side of the car, well, it's curved so you can see more of it. But you definitely want it to be a convex one because, remember, the concave one tended to produce a lot of upside down images. That would be difficult to see. But it also says on that mirror that objects in the mirror are closer than they appear. And that's because the image is reduced, making them look farther away than really are. So I'm not going to do the rest of the examples of the convex mirror because it's doing the same thing over and over again. But I highly recommend that you practice doing the remaining ones. Okay, so that's how to deal with ray diagrams and curved mirrors. Okay? Again, in another lecture we'll look at sort of the math way to do this. Okay? All right, we'll see you next time.